Hi guys, I wanted to follow up on the simple harmonic motion lab. I think by this time the cat's out of the bag as far as the equations that are on the AP exam and also in the text, and you can see them here on the screen. Some things to keep in mind with these two equations, and that's the reason for the asterisk and the pound sign, is they come with some assumptions. So let's talk through the assumptions that are in the simple harmonic motion equation. First, it is assumed that we're dealing with an ideal spring, meaning it has zero mass and that no energy is lost to heat in the spring itself. It's also assumed that spring is linear, which comes with it Hooke's law. And by definition, simple harmonic motion is when the restoring force, in this case, the force in the spring, the restoring force is proportional to the displacement of the mass and therefore the change in length of the spring. In this case, that they are proportional to each other. Here's the proportionality constant that we call the spring constant. And also for simple harmonic motion, that the direction of this restoring force is in the opposite direction of the displacement of the mass. All of that satisfied here for an ideal spring with Hooke's law. Now, going to the data, one of the things that you guys appropriately noticed when looking through the data, when all other things were held constant and we just changed mass, here's mass versus period, we get a relationship that shows that period is proportional to the square root of mass. This is very close to the square root to the power of approximately 0.5. You also noticed that we have an inverse power relationship. This is the graph that shows period versus K, and clearly showing an inverse relationship and to some power. It was probably a little puzzling that this wasn't K to the negative 0.5, which kind of leads to there must be something wrong with an assumption that we made about K, which I'll get to here in a second. You also appropriately notice that there is no relationship between amplitude and period, as is shown here. Essentially, this is a zero here, so there is no relationship, which is probably a little puzzling to some, because if the mass has farther to travel, shouldn't it take longer? But also remember that as the amplitude is increased, so is so is X for the spring. So the restoring force goes up. So those two have farther to travel, but the restoring force is larger. Those two factors must balance each other out. And as I mentioned in my solutions notes that I posted to you for a few days ago, G doesn't come into effect because it essentially doesn't change over the course of the entire experiment. And so you can see the period versus G down here graph, that the periods are punched very tightly for any given little g. And we can see here this is essentially zero. Again, there is no relationship between T and G. So looking at the suggestions that I received in the post lab, hey, let's try square root m over k. And so this is allowing mass to change. So we made the assumption that if K is on the fourth mark, I made the assumption, I should say, that when K is on the fourth mark, let's assume that we have a K of 4 newtons per meter. And you can see we have a nice linear relationship. However, we would expect this constant out front of square root m over K, we would expect that to be 2 pi, and that's clearly not. So something is amiss. And we also notice that nicely this intercept is pretty much zero. When you look at the period versus changing K, so this is our K value down here. I'm sorry, this is square root m over K if we have a changing K value where the m was a constant. Again, a pretty good, but not great linear relationship for period over square root m over K. Notice that it has some curve to it. Once again, kind of highlighting the fact that we might have something strange going on with our assumption about, hey, if we're on the fourth mark on the K slider, that means 4 newtons per meter. So that was some stuff we needed to figure out. So I pulled that data over to a new spreadsheet, and I started taking a look at the data. And what I did was I took the K and the T data, and I pulled that over to a new Excel spreadsheet, and I sorted it. So all the ones and all the 2s and all the 3s and all the 4s in this column were all together. And I found out, I'm pulling up the right one, I found out that if I used this equation here, whoops, let me get back to it. When I used this equation here to predict what the K was, what did the HTML5 PhET think the K was? And I noticed that when slider was on 1, then I assumed that the K was 1 Newton per meter, was actually closer to 3. When it was at 2, slider 2, when I assumed it was 2 newtons per meter, it was actually closer to 4, etc. When the slider was on 10, it's actually 12. And you can see in this graph over here, it's a nice linear relationship between the new calculated K and the assumed K, nice linear relationship. So in other words, when the slider is on 1, K is actually 3. When the slider is on 2, K is actually 4. When the slider is on 8, K is actually 10. When the slider is on 10, K is actually 12. So I used that, armed with that new information, I went back over and I changed this, the changing mass versus period graph, and the square root m over k. If I click on that cell, you can see that I'm using, hey, what's the mass in A2 divided by the fourth tick, which is what we used when we were changing m. We used the fourth tick, which corresponds to 6. And you'll notice here that even though it's not exactly 3, it's not exactly 4, it's not exactly 5, I am going to go with the assumption that the designer of the PhET didn't use this number, didn't use that number, didn't use that number, but used 3, 4, 5, 6, etc. And any kind of error in this number probably came from our mismeasurements of t, or we didn't actually put the sliders in the right place, etc. Hopefully that makes some sense. I also then went over to the changing k versus period data, and I updated it. If this was our assumed k, this is now our new corrected k. If this is our assumed k, this is now our new corrected k. I could have renamed this column here slider location or something, because when the slider was on 7, k was actually 9. So I used, in this column here, I used the corrected k value. So I have 0.1, which is what the mass was when we changed k, divided by the corrected k value and took the square root of m over k then. All right, and then we'll compare those two graphs. So here is the graph that goes with this data. And you'll notice that if we plot period versus square root m over k, where k was fixed at at 6 meters per second, and we changed m, we have this nice linear graph, really good fit, intercept of almost 0, and a constant out front that's really darn close to 2 pi. 2 pi, of course, would be more like 6.28 and some change. So it looks like we have a nice fit when we correct the k that matches what we've seen in the book or any other research that you did online, etc. So going to when we allowed k to change, so this is the data where k is changing, where mass was constant. So this is square root m over k for when k changed and m stayed constant. Again, an intercept of very close to 0, constant out front that's really darn close to 2 pi. And it's a really nice, get out the way there, a really nice linear fit. And so now that I've corrected the k's, you can see how your suggested the relationship is square root of 2 pi times square root of m over k should be equal to t. It looks like our data is working out just fine.